Okay, maybe without further delay, so I'd like to first welcome our speaker, Dr. Fang Li, of today. So she is a research scientist at the Worcester Polytechnic Institute, WPI, and he has been fire engineering, working in the industry for many years, and he's currently a fellow of Society of Fire Protection Engineers, SFPE. And she also holds a professional engineer license in US. She has like more than 20 years of experience working on different infrastructure in US and Asia. And she also published one book recently about tunnel fire protection design. So I think today's presentation will be very interesting because Dr. Li will share her first-hand experience about design some Shanghai tunnel project that is accomplished recently. Okay, so Dr. Li, the floor is yours. Could you share the slides?
Okay. Yeah, I did. Can you see?
Yes, looks good.
Okay. Good morning, everyone. Actually, I'm based in Boston, so it's nighttime here. I'm very grateful for Dr. Huang invited me to give the presentation regarding the fire safety engineer of tunnel system. My topic here today is fire protection engineering application to benefit China's leading development of the large transportation system. This is a book Dr. Huang mentioned about, I published last January, which has been delayed for 2 years. And the reason I have the initiative with this book was the idea I have been working with some of the large airport, light high-speed railway system, and the tunnel fire protection design. So all those project experience make me think maybe it's a good idea to have my personal first-hand experience and the knowledge to share with my peers, and maybe bring everybody's interesting and update to what current level the fire safety for the large transportation system in Asia, because Asia is having construction booming, particularly with large infrastructure as well. And I believe this is a future trend, continue going. Today, my focus will be on the fire safety design for the tunnel. When I published this book, at that time, when I start drafting this book, which is 2018, and currently at China at that time, about 16 cities have opened urban subway system, and moreover, 24 cities are building or planning to build a subway system in the future. So you can see the number here from 2011 and towards end of 2017. The number is really increased about 120%. And the last few years, because everybody knows the pandemic reasons, delayed this. But I'm sure this delay slowdown will cause another very high peak and booming in the future when everything go back to normal. So we can see we call it the China speed. And a lot of cities in China, because the traffic and the people's living style changed, and required to have a very efficient transportation system to be available for the public. So I think the government really put a lot of effort to this and building all the big infrastructures, including airport and the subway system. And particularly in some of the cities like Shanghai, the river cross the city region and cause a lot of tunnel system on the ground to make this transportation even more efficient. So this is one of the picture I can share. This is the left one is the city of Shanghai, very similar to Hong Kong somehow. It's a big metropolitan city. And also it's very beautiful city as well. Economic, large people population and very dynamic cities. But somehow we do need a very efficient transportation system. And in Shanghai particularly, the old city, Puxi, connecting to the Pudong, at least for over 12 tunnels and bridges, which is not enough yet. They're still building the connection between the two areas to make people's connection even more efficient. So the red one, the picture on the top is the bridge, and the bottom is the tunnel. So it's a very dynamic and challenging geographic situation as well. We can see, not even mention about the tunnel itself. All these surrounding areas brings challenge about what we can do for traditional fire protection system. And in recent years, there has been much focus on tunnel fire safety, partly because due to some of the spectacular incidents that have occurred, and partly because of the increase in construction of tunnel system worldwide. There is a clear connection between resolving the traffic problem in large urban cities and the need for more tunnels. Interruptions in the traffic through such tunnels create economic losses and delays that may have severe impacts, such as transportation of merchandise and people. I think everyone maybe still recall the big fire incident happened in the New England, the England Sea, which decades ago, and really bring people's concerns about what we can do if such incident happened again, because right now people rely on this even more. Fires are major risks that can create devastating effects. Expansions in the transportation sector and the ensuring pressure on traffic system forces construction of more complex and complicated underground system. This in turn requires new fire safety engineer solutions that need support and validation before even putting into use, which is, of course, that's academic side and the engineer practice working together to make this happen. Now we look at what we have in the code standpoint. NIPA 502 standard for road tunnels, bridges, and other limited access highways. National Fire Protection Association published the 2014 version. And the Road Tunnel Manual, World Road Association, which in France, 2011. I just list the two of those. This particular talking about the tunnel system. In China, when we do the road tunnel system, in Shanghai, the Chongming Line, the case study I'm going to present, we use the Shanghai local standard road tunnel design code, which published 2017, which quite updated. And it's a local standard, that's why they call it DJ rather than the GB. And it's issued 2017, effective 2017 November. It's a local Shanghai standard, but has been referenced nationwide. And this is some other related Chinese code related to the large transportation system I listed here, just give people idea. It's some other code available there regarding the roadways and other large transportation system. So in China, they do have a lot of different set of the tunnel system design and the railway road system design. And some may be published by the Ministry of Construction, some may be published as the standard point, as code. So when we do in the design, we found the core code standard as the design base, but somehow we have to look at some other available reference locally and nationally, and sometimes even international code to find the best solution to tailor the design, because the challenge we're facing, some code might not available to address those issues. This is some other regarding the like airport, and this is similar when we're talking, when I wrote the book, I used the reference as the code related to the airport as well. When we're talking about the tunnel system, one of the key points is smoke control system, because it's a tunnel, it's all underneath, and the smoke even generated above the ground have challenge to get out. Not even mention about the tunnel is totally underneath, and some may be just the road condition, some may be surrounded by the water. So find the way to get smoke controlled, confined is very critical for both the people in the train, in the vehicle, inside and outside. So it's very critical. We have a very engineered sound smoke control system for the tunnel fire safety design. This is a screenshot for one of the, it's a NIPA 502, it's a tunnel design. And this is chapter 11. And maybe you can see emergency ventilation should be sized, ensure the fire safety is not compromised, even with one fan out of service. So we have to consider about the reliability issue, consider about the worst case scenario, not the ideal situation. For smoke control, the emergency ventilation system shall provide a means for controlling smoke. So we're talking about control smoke. We have to realize the smoke generated, we cannot just put it out. It's there, but the best way to make people egress safely is controlling the smoke to confine in a certain space. So give people enough time to safety egress. In all cases, the desired goal shall be to maintain a tenable environmental condition in the evacuation path for motorists who are existing for the tunnel and to facilitate the firefighting operation. The reason I gave the screenshot for this, because I want to explain some of the concept here. I know a lot of audience are from practicing engineer, but maybe some maybe not very familiar with tunnel design. In tunnels with bi-directional traffic, where motorists can be on both sides of the fire site, which we double direction tunnel, which is the most current recent situation. The following objectives shall be met. Smoke stratification shall not be disturbed. Everybody know if we have a high speed velocity, somehow it will really negatively impact the smoke direction. So we have to be careful on that. And the longitudinal air velocity shall be kept at a very low magnitude. Smoke extraction through ceiling openings or high openings along the tunnel walls is very effective and shall be considered. In tunnels with unidirectional traffic, where we said one directional, the motorists are likely to be located upstream of the fire site, which means, the smoke, when the smoke occurred and when the situation is always the smoke spread in the downside. The following objectives shall be met. Longitudinal system control back layer distance, which is very important for the not preventing smoke going up by producing an air velocity in the direction of traffic flow. That means we give fresh air and make the area smoke-free. Minimize the disruption of the smoke layer. Transverses or reversible semi-transverse system, which is maximum exhaust rate in the ventilation zone that contains the fire and minimize the amount of outside air that is introduced into the zone by a transmitter system, created an airflow in the direction of traffic flow by operating the upstream ventilation zone with maximum supply and the downstream with the maximum exhaust, which makes sense. We try to create a confined smoke in that particular area and using the air, fresh air to make the people's area smoke-free. So all this concept and all this approach has been addressed in the code as the good reference when we're starting to look at what our tool will be. So we look at the code, what the code language there, what the meaning of there. Previously, systems were designed assuming a continuous traffic flow throughout the tunnel. That means, even with fire occurred and the traffic flow, the train still on the speed, is not stopped. A longitudinal ventilation system with jet fans on the ceiling could slow most of the problem associated with control of heat because we're trying to get smoke out without the fans at the top of the ceilings. Assuming that the traffic on the downstream side of the incident site could simply drive out of the tunnel, that means the ideal situation, there's no, crowded and all the trains packed each other. This is very ideal situation. Through prevention of smoke back layer, which means, we have fresh air in the upstream, tunnel users on the upstream side of the incident could easily escape from the tunnel through a smoke-free area. That's our ideal situation, try to make a tenable situation for the people occupant to egress both sides, from downside and from upstream side. Semi-transverse ventilation system where the heat and smoke are extracted from the ceiling, or transverse ventilation system where fresh air is evenly supplied and hot smoke extracted along the tunnel are not as common today because there was some decades ago, and it's talking about the one direction, properly designed semi-transverse system can solve the fire problem related to the queuing situation. As a confined region where the smoke may still exist in the tunnel, but because of the surrounding area, except that smoke zone, all the other areas is smoke-free, so the egress tenable situation can be maintained, and thereby increase the opportunity for evacuation on both sides of the incident site. Using both a semi-transverse ventilation system and a water spray system is a very safe solution, but of course, rather expensive. You can imagine, particularly with the long tunnels as right now, it's much longer than what we have, the code as before. So therefore, a longitudinal ventilation system in combination with water spray system is a more frequently practical solution from economic budget standpoint and performance as well. So this is the image I can give, maybe people can get a better idea of how that works. This is traditional smoke control strategy for interzone tunnel. You can see this is the one train situation, that's railway station A, railway station B, and the fire occurred between those stations. And only one train will be stopped there, and the fire happened in the front of the train. And also they have scenario about the fire happened on the bottom of side. All those different situations will bring different scenario and even have one system really should demonstrate doesn't work well. In fire, it is assumed only one train will be stuck in the interzone tunnel between two railway stations. The smoke control strategy will be based on the train driving direction, fire position, and the travel distance from the train to the nearest railway station. So all these factors plays roles in how the end of which system will be chosen with the best performance. This is the true train will be stuck in the long interzone tunnel situation. And we will add smoke exhausting shaft in the middle of the tunnel just because this is a two train will be there. If we want to smoke accumulated in the zone, it will really impact the another train, which is not the origin of fire started. For super long tunnel on the river, it is impossible to add a smoke exhausting shaft between. This is the case I'm talking about the Shanghai subway Chongming Line. This is the bridge on North Seaport and the tunnel on the south part. So this is a very complex system with subways, with bridge and tunnels as the whole entire project. The tunnel and bridge are built and put into operation for highway in 2009, and the Chongming Line will share the tunnel and bridge with highway. The length of South Tunnel is about 7 kilometers. So this is almost have everything. It's very complicated infrastructure system. For super long tunnel on the river, like I mentioned, it's impossible to add smoke exhausting shaft only because of the condition. And this is the section of the Chongming Line. You can see the center of the section. It has the reserved space for the future subway system and a highway with 3 lanes. So after this has been completed, it's a very advanced transportation system connecting the different region, different area. So this is one of the key project at that time. This is a fair engineering study we have been conducted to help evaluate and select the best system which works the best for this scenario. When train is stopped, we see the preliminary heating area, the fire origin is in the front. And the direction of the mechanical ventilation, we see the green arrow, which towards my right hand. Before the mechanical ventilation started, because we have time to detect the fire, and we have the time after initiate the smoke exhaust system before it go into the full operation mode, it's really take time. So during that time, the fire may be started and the smoke accumulated. So after we initiate the smoke control system and the mechanical ventilation started, and we have the choice. We have mechanical ventilation in the front, which we call the forward mechanical ventilation, and we have the backward mechanical ventilation, which is the bottom scenario. From all this simulation, we can see from the temperature rise standpoint, the backward mechanical ventilation, when fire source is located at the head of the train, backward mechanical ventilation will provide fresh air and cause fire spread to the train, which is regarded as fire load and aggravative the fire hazard. So forward mechanical ventilation strategy, it seems works better compared with the backward. So this is the correct choice for this scenario. When train is slowed down, we see the left image here, the figure. We give the different train speed as the red line, and the forward airspeed and the backward airspeed. For phase 1, phase 2, and phase 3, it has different meaning. The speed of train is faster than the speed of tunnel one. Smoke will go backward. At phase 2, the speed of train is slowed down to 0. The tunnel one still exists. And faster than speed of train, the smoke will go forward. This is the piston effect. For phase 3, the speed of tunnel one slow down, smoke will go forward and backward. So the smoke actually go both directions. When train is slowed down to stop, so that's a more detailed image about what I addressed before. The speed of train is faster than the speed of tunnel wind. Smoke will go backward. So that causes the smoke spread movement different direction. When trains slow down and driven by piston wind, the smoke move forward and reach 330 meters away from the fire source. It's quite fast. And the smoke movement in phase 2, which is the train slow down and the wind speed getting higher, relatively higher compared with the phase 1. And the last phase is the train stopped, smoke spread on both directions. This is without mechanical ventilation, which means when we have the fire detected, the train stopped, but the ventilation is not initiated yet. Based on the time, running direction of train is towards the arrow of red. And after 20 seconds, the train began to slow down after it detect the fire. The smoke front is 300 meters away, and the train totally stopped, which is 80 seconds, and the train about 270 seconds, smoke spread on both directions. This also showing the different scenario when the mechanical ventilation is forward. It gives a different temperature comparison as well. This is the ventilation for mechanical ventilation backward. We want to make a comparison which scenario is the best after the fire has been detected and the smoke control system activated. Which way is the best depends on, like I explained, where is the fire origin, where the train speed, where the train direction, and how the people located. And those all give us consideration about what's the best scenario and the solution for smoke control system. So the left scenario, scenario 2 is a mechanical ventilation forward direction. And the red one is the mechanical ventilation backward. You see it's quite different. With the left one, the temperature rise. The first one is driven by piston wind and become quite stable, all those different lines. And for the backward, it's really become very turbulent because it's inject refresh air, really make a lot of turbulence in that scenario. This is the conclusion, a summary, what our findings will be. From the left column, you see the position of fire. The fire we are assuming it's not in the carriage itself, it's outside. At the head of the train, at the middle of the train, at the end of the train, last one is the fire location is not clear. For option 1 is the current smoke control. Direction of ventilation could be changed. That means we want to make the system smart, which means it can be flexible, depends on what we think the best. So the ventilation system could be changed based on different scenarios, such as after fire position is confirmed, the direction of ventilation will be forward, which we said backward is not the ideal situation. After fire position is confirmed, the direction of ventilation will be forward. Half of the guests need to travel through the burning carriage. The egress time will be longer with risk of fire burning through the carriage increased. After fire position is confirmed, the direction of ventilation will be backward. Smoke will go back through the train and the time will be last about 8 to 15 minutes. Guests need to endure the smoke and evacuate under this situation. Fire size and hazard will be increased with the time of smoke going back increased. The last one is when fire location is not clear, fire position cannot be confirmed, the direction of ventilation will be forward. We assuming we just not know where is the fire, but the forward mechanical ventilation will be confirmed. For option 2, optimize the smoke control. Only one direction for ventilation. No need to identify the fire position. That means we save time because we don't need to, evaluate and make the judgment of if we want to the forward or we want to the backward. We make it simple. Start forward ventilation directly. No need to identify the fire position. Start forward ventilation directly. And no need to identify all the same, just because we want to optimize smoke control, make it more stabilized. The note we put here, the final direction of ventilation is same, but option 1 need additional time to identify fire position. The fire risk of fire burning through the carrier will increase because we waste some of the time. In option 1, if gas can endure smoke for 8 to 15 minutes, and after that, the evacuation environment will turn better because the smoke exhaust system start working. The final direction of ventilation is same, but option 1 need additional time to identify the fire position. The time is based on on-site fire command because we're not known where the fire location is. So this is the image about the evacuation tunnel, the opening ratio between the evacuation tunnel, which is adjacent to the tunnel itself, of the train tunnel. The opening ratio is about 28% because we want to keep a reasonable ratio about the opening connecting between. We don't want to make it too big, benefit one factor, which is maybe hurt another factor. And we see the evacuation tunnel, the train tunnel, and the stair based on our simulation, what is the best time and what is the best result. If we have a fire in the front of the train itself, and this is the opening between the train and the evacuation tunnel, which is the doorway on the front. This is we use the CFE modeling to evaluate the impact when two trains are stuck in the tunnel, which I presented in the previous slides about that situation. As one train is stuck at the back of the burning train, the results show air velocity is changed from assumed 3 meters per second to 2, because maybe based on some other factors we have to identify. This is the evacuation simulation result we see from scenario. We have here we list about 10 scenarios. Detection time is the same, alarming time is the same, but the difference, the time for leave the train is different. And we have time to reach the highway above the train tunnel is different. So this is quite a complicated analysis to try to give a full picture of what possibility of the fire location with regarding the evacuation. So we make the summary, make it short. The train shall try to go forward to next railway station. If train lost the power and be forced to stop in the tunnel, per the study of smoke movement by piston 1, in order to prevent increased fire hazard and improve the efficiency of fire management, following suggestions are proposed. Adopt one direction, forward direction ventilation as smoke control strategy. Provide smoke detection in vehicle, which make the detection even more faster. Improve fire resistance reading requirement for the material used for train carriage. Limit the range of door openings. Advise to open the doors at the end of the train. Recent development in water spray techniques, the sprinklers, water mist system for protecting of tunnels, because everybody knows in the NIPA 502 regarding if we want to have sprinkler system in the tunnel, it's not clear because still have debating how that impact the smoke exhaust system. Even it can benefit cooling the environmental and maybe also help the people to egress. For protection of tunnel, it's of course, which seems like a positive reaction to the need to minimize the risk and the consequence of fires in tunnels. In urban road tunnels, there is a new type of hazard, namely constantly increase the queuings, which has forced the searching for new solutions to existing safety problems. The large-scale testing of water spray system and the research that has been performed in relation to such testing has improved our understanding of these issues and helped to debunk many of the myths associated with the use of water spray system in tunnels. The main question today concerns technical trade-off and the maintenance cost together with reliability issues. Traffic control issues and the detection of fires in relation to the use of water spray system still need to be resolved properly. The challenging issue for the fire safety engineer community is associated with technical trade-off when installing this system. Should the design fire for the ventilation system to be lowered from, say, 100 megawatt to 5 megawatt? That's really give motivation and benefit if people want to have that system in this place. If a water spray system is installed, this could reduce the investment cost of the ventilation system considerably because we lower the proposed fire size. An example of such decision is found in the new bypass project, which millions of dollars have been saved in initial costs. But this, all the sort of ideas has been further studied by our engineers and academic community to make everybody recognize is the reasonable approach. Further, should the required structural fire load be reduced if a water spray system is used? The tendency at present is to pose that it should, but many are of the opinion that one must guarantee the reliability of water spray system before such technical trade-off can be allowed. And the additional trade-off, which is discussed in a reduction in numbers of escape road used in tunnel when a water spray system is provided. Because everybody knows when we build a project, the budget is very sensitive, the problem and issues, and we have to face this rather than try to avoid this. Each of these questions is very important, but neither of them has been very fully addressed in large-scale research projects. Design fires for tunnels with water spray fires have not been dealt with in guidance or regulation today. The effect of water spray on fires related to new energy sources, electrical, hydrogens as well, has not been tested so far. There is clearly a need for research dealing with these issues in the near future. In real and metro tunnels, the situation is different. The requirement for material used in rolling stock make it easy to deal with fire safety issues, although the latest large-scale testing carried out in Sweden and Canada indicate a very high heat release rate for burning trains. So properly designed carriage can minimize the consequences of fire, but the consequences can be large in mass transportation system. The interior lining materials, luggage, and ignition source are very important parameters in determining the fire development. Also, the compartmentation and quality of outer compartmentation, like windows or the window steel body, plays important roles in the risk of a fully developed fire. So there's still a lot of unknown. Even we have a lot of projects already can be learned. But it just means academic side, we have a lot of questions need to be addressed and initiated from our academic side as well. The trend towards open gangway trains with no separation between 3, 6, or more carriages has created new challenges for the fire safety authorities. There is no large-scale test performed on that address. Future research should focus on new type of carriage with long open gangways and trains with other types of bodies than steel, such as glass fiber or other lightweight materials. Fire safety in road tunnel and rail tunnels require completely different approach, as the material and the fire performance requirement of the vehicles, as well as the number of users, are very different. The fire dynamics, however, are very similar. The challenges in future fire safety design require better education of fire safety engineers in the fire dynamic internals. So this is a case for Chongming, and also a side issues. I want to give a quick update about the vehicle base of Shanghai subway line, which means, you see, as the entire vehicle base is covered by shopping mall, it is very hard to add a smoke exhausting shaft in the middle of the vehicle base and the design of smoke compartmentation based on China code requirement. So with that, we're using the SFPE modeling, and we created using the logic smoke zone rather than the physical smoke zone. We call it a logic active smoke zone, trying to create an air supply and smoke exhaust, trying to using that because we have a good condition about the high ceiling space. Top space can be regarded as smoke storage. We achieved that using this concept with the airport, some other big areas. So smoke reservoir could be a very good feature to implement it. So with that case, very short, just give ideas about a lot of issues we have been facing when we're talking about the transportation system, even tunnel system, subway system. They have some similarity, but also they are quite different regarding different fire scenarios and the system we're proposing. And this is the main content of my presentation. And thank you for your listening.